So this is the Zoom. This is
no. To go back and forth. Yeah, this is the Zoom. Yeah, you would just click on.
I do my.
Okay, it's 2 o'clock, so we should get started. The first speaker this afternoon is Stefano Bolognesi, who will tell us about strong and chiral view.
Okay, thanks a lot for the invitation. It's very nice to be back when I did my postdoc here. And I'm going to tell you about our work I've been doing in the last years with Ken Konishi, you know, and very good PhD student, Andrea Lucio. So this is the plan of the talk. I will tell you about a certain class of SUN strongly coupled chiral gauge theories and discuss the properties of the entire class and discuss in specific examples. I will focus on the structure of the symmetry group, the gauge group, the global group, the zero form symmetry, the one form symmetry. And then we will discuss all the possible IR phases, the confinement phase, dynamical leaks mechanism, in particular among dynamical leaks, the two are color flavor locking and dynamical abelianization. Then I will describe you a little bit about manifestation of the strong anomaly in the effective field theory and general lesson and open problems. So this is a series of work we have been done. We started working this subject in 17 with Misha, Shifu, and came to Pisa. It triggered our interest in this topic, and then we continued working on it. Most of the new things I will present is on a work that is in preparation, and we are actually developing many of the ideas that were present in the first paper. We just take to the extreme consequences all these ideas. So the class that we'll describe is very simple, is SUN gauge theories. And we put 3 conditions. We want gauge anomaly to vanish. We want positive beta functions so with strong dynamics in the infrared and dynamical scale. And we also require the possibility of having Lagrange limit. Okay. So this is the representation we can choose: symmetric, 2-index, anti-symmetric, anti-symmetric, anti-anti-symmetric, fundamental, anti-fundamental. Okay. And we will mix them. So this is the way we call them. We will use this jargon. So I will introduce this jargon to you, where we always use in our papers. So I will use it even if I don't want to. So it's better I introduce it to you. Whenever I use psi, I always refer to fields in the symmetric 2-index symmetry representation. When I use chi, I refer to fields in the 2-index anti-symmetry representation. When I use eta, I refer to field in the fundamental representation. Okay. Now, in general, all these theories have a gauge group and a flavor group. And the infrared spectrum contains number-Boson bosons, massless bosons that are required to be there by some symmetry breaking conditions. And there are also massless fermions that are required to be there by anomaly Toft matching condition, okay? So in most vector-like models, like QCD with fundamental, anti-fundamental, or antisymmetric, symmetric QCD, this vector-like model belongs to this class, okay? Among this class of theories, there are also vector-like models, symmetric QCD, antisymmetric QCD, fundamental QCD, and a lot of other chiral theories. In most vector-like models, so what happens is that you have gauge invariant bifermion condensate. And you can, with condensation of gauge invariant bifermion condensate, break most of the anomalies that have Toft anomaly. And that's what happens usually in the solution of this problem, no? You have condensation of bifermions, gauge invariant, and this most of the time solves the Toft anomaly matching problem. So in chiral gauge theories, this is not always possible. Sometimes you have gauge invariant bifermion condensate, but even if you have them, they're not sufficient to solve the Toft anomaly problem, okay? So Toft anomaly problem in this theory can never tell you exactly what is the phase in infrared, but it's very constraining. It's very constraining so that there are very few reasonable solutions that can happen. You can never say that they're the real one, but if you want to construct a different solution, then you have to assume very intricate condensates. Yeah, you can have multifermions. I consider this a little. Yes, you can have gauge invariant 4 fermion condensate, for example. But it's hard to construct to break all the anomalous theories, anomalous symmetries with that. Okay, it's a possibility. Yeah. Also, another topic we will discuss is strong anomaly. How strong anomaly is realized in infrared? By strong anomaly, I mean, roughly speaking, doing Toft anomaly matching with anomalous symmetry, roughly speaking. So, yes, yes. No, no, well, we take theories that have yeah. Okay, yeah. Yes. Yes, okay. Modular anomalies that are not yet, gauge anomalies that are not yet discovered. Yeah, I remember. Yeah, and now and I talked to yeah, and he told me that well inside himself. Yeah, just no, we discussed it. I remember that's something that's wrong. Yeah, but now David don't talk us about this, you know, yeah. Yeah. So it could be also some kind of from the positive that straight construction guaranteed that
once we're speculating, they're unknown. Maybe they're unknown. Yeah. Unknown unknowns are very powerful. Unknown unknowns are very powerful.
Could I ask a question related to the topic?
Okay.
So can you repeat? Did you say strong anomaly or anomalous symmetry?
It's about the strong anomaly in the UV. Okay, the U1 axial anomaly, how it's reflected in the infrared, like the mass of the eta prime. Yes, roughly speaking, it's not really Toft anomaly matching. It's not rigorous.
Can anything be said about
It's not a rigorous argument, but like CAQCD. I will tell you what. Yeah. It's like the axial anomaly due to the strong gauge group. Yeah, the anomalous symmetry. So usually Toft anomaly matching, you do it with the real symmetries. The anomalous symmetries, you don't consider them. But anomalous symmetries can tell you something about the infrared. It's not completely rigorous, but they can tell you something. Okay. So this is the first prototype in this model. Is a theory with one symmetric in the two index symmetric, and to compensate the gauge anomaly n+4 anti-fundamental. And we always call it psi-eta model. Psi is this, eta is this. So here there are two U1 symmetry, U1 psi, U1 eta. Only one combination survives the strong anomaly. This is a non-anomalous symmetry, U1 psi-eta. And the symmetry group is the following. They have a gauge part. The flavor part is the SUN+4 of the n+4 etas. And then this you have this U1 non-anomalous. Okay, actually the group is a little bit more complicated. Well, it's smaller than this. This is a covering space of the group. The real flavor group is this when n is odd, and this when n is even. So the best way to understand this is to go one step higher and take the two U1 symmetries, U1 psi and U1 eta. And you know that is in this U1 symmetry, there is a discrete part that is unbroken. For example, in U1 psi, this is the graph for n equal 3. You have a Z5 that is unbroken. For U1 eta, you have a Z7, n+4. But these are not independent. They're all contained in this non-anomalous U1 that winds around the torus and hits all the discrete symmetry. So once you consider the U1 psi eta, you also automatically consider all the discrete part. But if you want a global representation of the group, then you have to divide by the center of the gauge group. The center of the gauge group overlaps with a certain Zn group in the flavor group, so you have to divide. And this, because there is a, yes, but then there is also a Zn here that acts on fundamental in the same way. And if you take this and the inverse of this, they don't act on fundamental. Yes, exactly. And for n even is lastly the same, but this non-anomalous U1 does not hit all the discrete groups. It hits only the even ones. So you have to add a Z2 that is fermion Z2. This D2, this group is not really disconnected. Okay, this D2 you can write it here. You can bring it down here. But anyway, the important thing is that this is roughly half the size of this one and is odd. Okay, so there is this structure that is a little bit more complicated than vectorial theories, but not too much. Then the other theories I will discuss is the chi-eta model, that is like roughly the same of the psi-eta model, but then this time you have two symmetric, two index antisymmetric representation, n-4 anti-fundamental. Then the same stuff, you have non-anomalous U1. The symmetry group is this. Now you have SUN-4 and non-anomalous U1. Then the other theory that is simple is the theory with 1 2-index symmetric, 1 2-index antisymmetric conjugated and complex conjugate, and 8 anti-fundamental. Okay, this theory as n+4 and -4, 8 satisfy the requirement of having 0 gauge anomaly. Here you have 3 U1s, one is anomalous, and these are the two combinations that are non-anomalous. And this is the gauge group. Or again, this is the covering space of the group. The real group is this. You have to write as Zn, and then Z8 divided by n star. N star is the greatest common divisor between n+2 and -2. Okay, now you can enlarge the spectrum and consider a bigger set of theories that I call n psi and chi. I can write it in this diagram. The one I consider are like that. This is psi eta model as one two-index symmetric and a number of fundamentals to compensate gauge anomaly. This is the one antisymmetric, the chi eta model. This is 1 minus 1. And whenever you pick one number, one in this table, one m psi and chi, then the number of fundamentals is that you have to add to satisfy the gauge anomaly 0 is this one. And if you consider the asymptotic free condition, you practically have all this set of theories, also the complex conjugated, that are good theories at large n. So in this big class of theories, I told you at the beginning I have this 6 representation to choose, and one zero gauge anomaly condition. Roughly, I can choose 5 parameters. One way to think about these 5 parameters is the following: you have to choose one number in this two-dimensional integral plane, the number of two-index symmetric, the number of two-index antisymmetric, and then you can decorate with a number of NF flavor QCD, a number of NS two-index symmetric QCD, a number of two-index antisymmetric QCD. So this is a way to roughly to think about this this family of solution. Okay. Yeah, this is the when you have only one symmetric and one antisymmetric, you can go up to 5 here. So this is the place you have to be at large n. Otherwise, you lose asymptotic freedom. If you start to decorate with QCD, then you have to be smaller. But so an example of decoration is this following models that are very old models. One is called Barry-Yankelovich model. One is called generalized Georgi-Glashow models that are models of a particular model of this set that essentially you take for the Barry-Yankelovich model, you take the psi eta model. So one two-index symmetric and n+4 antifundamentals, and add the p flavors of QCD, p families of QCD, fundamental, antifundamental. And for the generalized Georgi-Glashow model is the same. You have one chi eta model and you add the p families of QCD. So these are particular models that are the same, more or less the same properties. You have two non-anomalous U1, you have this symmetry group. And I will tell you later why this particular set of model is a little bit special in the whole setup of this 5-dimensional, discrete 5-dimensional parameter. So among this model, there are 3 special ones without fundamentals. If you don't want fundamentals, then you can have symmetric QCD, antisymmetric QCD, or you can have these chiral models that are called psi-chi models. These chiral models are a little particular because you cannot scale n to infinity. They belong to this class, but they are part of this class, but only for a finite value of n when this is exactly equal to 0. And I will use these models later because they have some particular properties. For example, they have Z2 exact center symmetry. There is a Z2 center symmetry that does not act on the fermion. Then another nice thing that for when n equals 4k, they're purely bosonic, in a sense that you cannot construct a gauge invariant fermion operators out of this. Okay. Now we want large n. Roughly speaking, these theories enjoy large n, and they enjoy large n in a combination that mixes all the properties of usual large n that we are accustomed to. Okay, so we are accustomed of Toft limit large n when NF is fixed and n is tend to infinity. So you can think of mesons as open strings, and a large n they are weakly coupled, and you have in the massless sector a finite number of states of order 1. Then you have Veneziano limit when n scales like n, and the interaction is the same, but then you have an order n massless state. Then you have S and symmetric, antisymmetric QCD. Then you can think of a meson as a sort of closed strings, and they have the same kind of behavior. And the interaction is a little bit different. Okay, these models have, of course, as you expect, because they're a mixture of this. They can have all a mixture of this type of solution, okay? For example, the psi eta model can contain a gauge invariant variant made of psi and two etas. Psi is the two-index symmetric, eta is the anti-fundamental. You can think of this baryon as an open string. It's an open string of Veneziano type because this eta has n+4 flavors. And it's a fermionic open string. Then you can have mesons also, but you take psi, psi bar, eta. And for the psi eta model, you can do the same. You can do also these closed string mesons. So what we take from this is that they have a large n limit. In the large n limit, the gauge invariant operators are weakly coupled. There may be an eta prime. When there is an eta prime, most of the time his mass does not go to 0, but this is what happens. So roughly speaking, you can think of it in the large n limit. This is a qualitative thing, okay? It's not just an introduction. So one nice thing about the psi eta model, this is a thing that is very well known in the past. The psi eta model, of course, with this model, we ask ourselves, what is the yeah, yes, you can. I don't know.
Because that's a way of getting to decoupling and tracking what phases we get at.
Yes, that's true. Yes, but then so, okay, what you ask from this model? What is the infrared theory? Of course, you can guess anything you want, but you have to solve the Toft anomaly matching condition. And that's the difficult part. For the psi eta model, there is a very special solution. There is a confining solution in which you assume that the massless particles are just these baryons here, psi eta eta. There are this number of baryons, and they satisfy exactly the Toft anomaly matching conditions. So this is a very special solution in which you assume that there is confinement. There are massless gauge invariant fermions of this form, psi eta eta. They must be antisymmetric in the flavor representation, and miraculously they satisfy the Toft anomaly matching condition. So this type of solution of the anomaly problem is very special, is a little bit miraculous. It works in few other cases, but certainly is unrealistic for all the theories we consider in this set. Mm-hmm. Yeah. In this okay, but in other models it's unrealistic. Okay, if you yes, in other models it's unrealistic. It's unrealistic in the whole set of models I'm considering as a solution in the whole set of models. So another solution is to a dynamic helix. Yeah. Yeah, you can. It could be. Okay. Well, okay, there are also possibilities. There are possibilities of infrared theory. That, yeah.
Okay, you have to have a reason why there is this, why you suspect. If we have a band sax conform on to a small count, this is a but the strong count without special.
So the other type of solution that we consider is bifermion condensate, but you cannot construct bifermion that are gauge invariant, but you can construct bifermion that are charged under gauge, and that's what you can assume, that there is psi-eta condensate. And psi-eta condensate, the most simple way to do this condensate is to do it in a way that you have color flavor locking. So the gauge group is completely broken, is locked with the SUN subgroup of SUN plus 4, and you have this pattern of breaking of symmetry. So you don't have gauge group in the infrared. All the gauge bonsons are massive. And what you have in infrared is a number of massless Nambu-Goldstone bosons, because there are a lot of symmetry breaking here. Then you have a number of massless baryons to saturate the anomaly, and everything works fine. So there is a distinction between this mechanism and the previous mechanism, if you want. This mechanism is a bit miraculous. You don't know really why this works, and you have just to try. This mechanism is automatic. You can always do it. Because whenever you have a bifermion condensate, you break, you decompose the fields in the unbroken gauge group. All the part that are vectorial gets massive, and what is left is your massless fermions. So you're automatic that this method gives you viable solutions of the Toft anomaly matching problem with the infrared free theory. And this infrared free theory is a theory that contains Nambu-Goldstone bosons and fermions. Now, the other models that enjoy this miracle is the chi-eta model, where you have one antisymmetric as n-4 antifundamental. In this case, there is still a miracle. There is a hypothetical gauge invariant baryon fermions that satisfy all the anomaly matching conditions. In this model, you can also do the color flavor locking and the dynamical X condensation, but this is a little bit tricky because when you do the condensation of chi-eta, you enter in a region that has exactly the same flavor group of the original theory. So this is a model that could be continuity, or there could be Fradkin-Schenker continuity or complementary with the model we discussed before. Now, this miracle of gauge invariant fermions that satisfy the Toft anomaly condition works only for special theories. In general, works also for this theory here, the Bar-Yankelovich models. So the one that you take one psi-eta model and you decorate with a finite number of QCD. For these models, the miracle works. You can construct these three sets of gauge invariant baryons. One were psi-eta, one were psi-eta chi. Chi is the number of fermions of the QCD part I had. Psi-chi. So for this model, there is a hypothetical solution of the Toft anomaly matching problem where the infrared is confining and you just have gauge invariant fermions. Is miraculous. I want to stress that it is very nice solution with just these three simple gauge invariant fermions. You can solve all these Toft anomaly matching conditions. Okay. You have these three sets of baryons. You have this B C eta eta. Okay, sorry. C eta eta. They're gauge invariant. This is 2-index antisymmetric respect to this group here. This is eta key. And this anti-fundamental, fundamental respect to this, and this 2-index symmetric respect to this. So they have charges under this. Of course, they're gauge invariant, but I didn't count them, but there were this. Rules out what? Why? But this is just fermions. I mean, they don't interact. They're gauge invariant fermions. I don't know. Well, anyway. So for this particular model, you can also have a. This is a model of the psi eta model decorated with QCD. You can have this sort of color flavor locking solution. Also, you can add a condensate of quark, anti-quark like in QCD. So you can always have this other route, other possibility, okay? Now, for these particular models I told you before, these two in the whole set I considered, okay, I told you roughly how to parameterize this whole set, okay? Okay. These two ones are very special, Barry-Yankelovich model and generalized Georgi-Glashow models. They are the only one for which there exists a reasonable solution in which you have confinement and no chiral symmetry breaking. So in which this miracle works. Why is that so? I try to explain you now. Take the other model that we are interested in, and I will focus in most of the talk. Take the psi-eta model, the one you have one symmetric, one anti-antisymmetric, and 8 item fundamental. So you ask yourself, can I do this miracle of constructing gauge invariant fermions that satisfy Toft anomaly matching condition? So what gauge invariant? Of course, you have this simple baryon psi eta eta that you can always do. You can make it as you can choose symmetric or antisymmetric of SU8. What other fermions you can construct? You cannot construct many other fermions. You can combine this. You can take 3 copies of this, but then it's very weird to have 3 copies of gauge invariant fermions that become massless. You can start to use the epsilon tensor, but then it's very weird to think that a composite N fermions become massless into infrared. So I think the only reasonable solution is to use this object here. Now, can you solve the anomaly matching condition? No, you cannot, because this SU8 cube Toft anomaly is of order N. Okay. And you cannot have gauge invariant fermions of order N because you don't have an order N flavors. You have only 8 flavors. So the only way to construct this hypothetical miraculous theory that confines gauge invariant fermions would be to assume that you have N, at least an N gauge invariant fermions in the infrared. And to have any gauge invariant type of fermions, you must use the epsilon tensor. You must construct a lot of weird baryons made of N types of fermions that you assume that become massless in the infrared, and it's very strange. So you could do it maybe, but it's unrealistic to be the right solution at large N. It is planarly equivalent, if you yes, but not There is this SUL theory that breaks the planar equivalence. Yes, the
There is an extra SUA. Of course, if you ignore the but if you accept anomaly, you have to mention too.
yeah, taken at face value, it is equivalent. Yes.
What is the theory in the topology of the SCD? Then you exclude these fermions and their effects and their model. Some part of the planar theory. Because when I say large n, what I mean is not a large n. Finding theories according to the partition function and going order by order according to the topology, not according to some number. To me, large n is not take a large number, it's a counting classifying diagrams according to the. Okay, and we have to match. What at the next level. Next level you will get stuff.
Yeah, at face value, it is a planar equivalent. It's planar equivalent to symmetric QCD, anti-symmetric QCD, but there is no gauge invariant by fermion condensate. So there is the phase will be different, but at face value, it is planar equivalent.
But the global spectrum or the color
Yeah. Okay. Yeah.
will be identical.
Yeah. There could be something, but
I think.
no, you can do it. You can do it. Yeah. A gauge invariant condensate, you must have a 4 fermion condensate, and for the 4 fermion condensate is in a joint of SU8, you can break it. So the 4 fermion condensate doesn't really solve the problem. Yeah. Okay. Yeah, I don't know. I'm telling about large n. I don't know. For any n, now I will tell you something. So the same thing is for all these other class of models. Whenever you start to add NF fermion antisymmetric or symmetric that is bigger than 2, you run into this kind of troubles. That if you want a solution that is reasonable at large n with confinement and no symmetry breaking, you must have an order n gauge invariant fermions. It's not realistic. So there is this nice example of this paper that came out recently. These people are interested in phenomenology. They take SU5, n equal 5, 3 families of Chieta model. Of course, it's the grand unification theory with 3 families. And even if they study then other phases, they give this nice example of a solution of gauge invariant fermions that satisfy Toft anomaly matching condition. You see, this A is what I call chi, this F is what I call eta. You see, you have this baryon, but you have a whole bunch of other baryons, and you need heavily to use this epsilon 5 tensor. So this is a solution that works only for SU5, and is completely unrealistic for large n. I think it's unrealistic also for SU5. They also say, okay, we have this solution, but we don't know how to use it. Just to tell you that, okay, this is, so you need, even if you believe in this nice, miraculous, they're nice, they're miraculous and very simple solution of confinement with the gauge invariant fermions, this cannot be the solution for all these class of models. So in particular, I will study the Chieta model. Chieta model is one of the first models for which you don't have this miracle. This is the first idea we had in 2017 with Misha. One possibility, not the only one, we're just throwing out possibilities, is to have condensation of psi-chi. Psi-chi, if you saturate two indices, become a joint field, and you want condensation to create an infrared field theory, and you assume dynamical abelianization. And you assume that there is zero condensate of psi eta. So this is one solution that solves the anomaly matching condition. In which way? This is a breaking of the group. SUN is broken to this UN to the N group. And then you have a flavor group. SU8 remains there. SU8 is untouched. How is solved the anomaly matching condition? Anomaly matching condition is solved. I don't know. This is.
Yes. There's something funny with this connection.
Maybe. Sorry.
Is your computer dead?
Maybe.
Okay.
No, it's not that.
No, it's not that.
It's resurrecting.
It's rebooted.
I don't know why.
Okay.
It's finished.
Well, time-wise, yeah, boundary.
Okay.
This is not quite how I. Oh, so. You know, the subtlety is putting pressure on Alicia because you know, she needs to go home at some point. And we didn't have the request, so obviously we're going to hurt her. But the more we push back, the more. But yeah, 5 minutes is okay.
The Russian side.
I advise against taking the light rain. But it becomes very
Okay. Okay, now it's back. I don't know if we can.
Okay. The laptop works, so now the question is whether this will work. I mean, we could switch to my computer, but it will be very funny. Like 1 minute.
Okay, you can.
Stefano, do you want to?
Yeah, I just show you the conclusions, but.
Did you send?
Yes, I sent you.
Okay.
Yeah.
Okay, I trust you, but I need to find you. You're there. Take 5 minutes. So this is.
Okay.
Okay, take another.
Okay, thank you. Okay, so I give you just a little bit of overview of what we are doing now, what we have done, what we are finishing. So we are studying this model of Psi eta model, and we assume dynamical abelianization. Okay, dynamical abelianization is condensation of this field in a joint, and they assume that there is n U1 field. But then in the infrared, you have a bunch of U1 with chiral fermions, psi and eta. And this chiral fermions that remains in the infrared is a chiral U1 quiver theory. They saturate the anomaly. And roughly, we had this idea many years ago. And what we have done recently is to say something more about the effective models. The effective model is this. We choose this particular set of generators of U1s. And there is also the anomalous U1 that we want to consider. And this is the full symmetry group breaking pattern. And then we discovered that this theory must have another massless boson. There is an Ambu-Goldstone boson pi that comes from the breaking of psi key symmetry. There is a U1 psi key that is spontaneously broken, is non-anomalous, and is spontaneously broken by the psi key condensate. And then there is a U1 tilde that is unbroken. Then there is the anomalous U1. So this is an interesting model because in the infrared, if you assume this pattern of symmetry breaking, you have a quiver U1 gauge theory with chiral fermions, one Ambu-Goldstone boson, and then you can have potential that must be constrained by an anomaly, and this is the only way to do it. And then we discovered also that there must be an action coupling, an action type coupling between this pion and the gauge fields. Yeah. Yeah. So how much time I have? 1 minute? Okay, the other thing that we discussed in the past is how to do the matching of the strong anomaly. What I mean matching of the strong anomaly? Matching a strong anomaly, I mean a very simple thing that everybody in this room knows about QCD. In the low energy effective action of QCD, if you take a U field of psi right, psi left, you have a would-be Ambu-Goldstone boson, that is the eta prime. The eta prime is the would-be Ambu-Goldstone boson of U1 axial symmetry, but it's not a Ambu-Goldstone boson. How it gets a mass? You can see the mass in infrared with this action, that is the Witten-Di-Vecchia-Veneziano action, that reproduces the strong anomaly because you reproduce the axial anomaly in the infrared. This action makes the eta prime massive and also cancel if m equals 0 the effect of theta. So you can see the effect of the strong anomaly in the infrared. So can we use this as a requirement for all theories that they must see some effect of strong anomaly in the infrared? Okay, this is not a theorem, so I don't think you can assume this, but you can see if in some theories something like that happens. For example, in all these models where we have a condensation with gauge invariant fermion, these miracles that can happen in these theories, then you cannot reproduce strong anomaly infrared because they're gauge invariant. But there is no, strictly speaking, problem with that because they don't couple to eta, to theta term, so you cannot do it. But we saw that this is possible. This very easy solution in the psi-eta model that I presented before, because in the psi-eta model, you have a bunch of U1s with a bunch of fermions, and the strong anomaly is exactly reproduced by the normal anomaly of the fermion with the U1s. So in this model, you can reproduce the strong anomaly very easily. And then we study also strong anomalies for the other models, and we saw the strong anomaly can be reproduced when you have a dynamical X mechanism. It cannot be reproduced when you have a confinement without condensation and without chiral symmetry breaking, but this does not rule them out. Okay, maybe I give you the conclusion because I kind of cannot skip talk about generalized anomaly. Okay, but this is an interesting set of theories that must be studied. Of course, we can use anomaly matching, strong anomaly, generalized symmetries, but then at the ultimate level, we need dynamical arguments, okay? Recently, there have been interesting developments in SUSY breaking. There were interesting works in the past about compactification. I don't know how much has been done after this. And of course, the interesting thing would be to use phenomenologically this theory. But since nobody knows what is the infrared phase, then we still have to study the theory of this theory.
We have time for one quick question.
Yes, yes, we have studied that. We never had real results, but we have tried. We tried. We tried. We didn't have to publish anything, but we are thinking about this. Yes. Yeah. Sorry for my laptop. My laptop.
This is the USB-C. Usually it just works automatically without any issue. And then pointer is our next speaker is Sergei Dubovsky from Mayu, who's going to tell us about the zigzag model.
Okay. I'd like to start with thanking the organizers for the wonderful conference. I really was enjoying my time here. And this talk is based on several works which I wrote in with Jack Donahue, who is a PhD student who will be applying next year. And he's good. And I have somewhat ambitious plan because you see my title is called quantization of the zigzag model, and it's last item here. That means I'm promising that I will get there. But hopefully people are relaxed and about to fall asleep. So I think I should make it. So I'll start with explaining how the zigzag model is related to dynamics of confinement in 2D adjoint QCD, then talk about classical integrability of the zigzag model, and then talk about quantization, which is the main, also that's the relatively new topic. So well, our interest is understanding dynamics of confining strings. So the setup we're thinking about, generally thinking about confining gauge theory with a gap, with unbroken center symmetry, and Lagrangian limit, so pure glue being a prototypical example. And in a theory like that, you may consider infinitely long string, it cannot break, and then study scattering, study bullshit dynamics on that string. And at finite n, so we get this two-dimensional theory which lives on a string, and it has a cutoff which where it loses unitarity due to the fact that string may self-intersect and produce closed strings, which are glue balls in the bulk. But the scale where it loses unitarity goes to infinity. One takes n to infinity because the pinching off of the short strings is suppressed. So I'm imagining, yes, I'm imagining our world, which is described removing fundamental quarks. Let's say there is pure glue sector. Then I can take in this room an infinitely long flux tube and study how it vibrates. And so, and that's what I'm interested in. And the point is if one takes top limit first, if one goes to planar limit, that kind of for this theory becomes boring. It becomes theory of free gluons. But the bullshit theory is still interacting theory, and it's unitary theory. And that's what I want to think about. So that's a basic object which stays there in the strict planar limit. Well, actually, So I said this limit one gets a microscopic two-dimensional theory this way. So in this sense, kind of confining strings, they become as fundamental as critical strings. So these are geometrical objects which cannot break, and that's what we want to study. And also, well, because it's a theory of fluctuating 2D geometry, one expects that it will be gravitational theory, and that's why it's hard to understand what it is. And that also shows that the natural observable to focus on is some on-shell quantity, which is a Walsh-T S matrix. So I'm thinking about, well, again, this long string, I'm just exciting it and scattering excitations and see what comes out. So that's the motivation. And well, we have a cartoon from our understanding of this. If the underlying gauge theory is asymptotically free, we have a cartoon of what one expects to happen in this theory at high energies, because we kind of know degree of freedom at high energies, which should be there on the world sheet. This should be just part of nonperturbative QCD. So in particular, if it's pure glue, high energy excitations, I should be able to think about them as gluons. And so I should be able, kind of the cartoon for high energy scattering on the world sheet is that one takes two partons, scatter them. Well, time goes here from bottom to top, so I scatter them. They go through each other. That's what QCD people would call hard collision. But if energy is really high, then not much happens here. So the two particles overshoot, but a string is still there because I'm in planar limit, it cannot break. And so one gets this time delay from the zigzag, which is drawn here. So basically the point of this talk is to try to put some kind of flash on this cartoon with concrete formulas in a simple model. Well, from the point of view of the worldsheet in starts at low energies from Nambu-Goto description, well, at low energies are really goldstones of the Nambu-Goto string, but at high energies they become gluons of QCD, and to some extent that's the central question: how to gluons, right? It's partons. It's pure glue that they are gluons, right? That's all what you have. No, because I consider this sector. I took exact planar limit and consider only the sector which then the string decouples from all the rest. So I consider excitations on a string, and so they cannot go into the bulk because string cannot break. Well, because there is nothing else. If I talk about QCD, so you may think about the string. Well, at low energies, it's a reason bond. These are Goldstone bosons. But if I think about this, let's think about the string as a heap physical. Let's put some fundamental, anti-fundamental quarks there. So I'm really studying the interior of heavy quark meson, right? And when we look inside heavy quark meson at high energies, what do we find there? We find partons, right? So yeah, adjoint degrees of freedom, right? Yeah, if it's pure glue, then it's gluons, right? So this is intuition, and kind of the purpose of this talk is to try to, as I said, to put some formulas behind that intuition. Sorry? Yeah. Well, at low energies, if I think about 4D glue dynamics, that theory would be described by Nambu-Goto. So this picture tells that what we think are Goldstone bosons of the string at low energies, at high energies, they turn into gluons. But yeah, so yeah, there is D-2. If it's pure glue, there are D-2 gapless scalars in this theory. Yeah. Okay. Let me move ahead. So this answer suggests, as always, when you have some short distance process and some long distance process, one expects the scattering will take some factorized form. So there should be some factorization. Roughly speaking, there will be some partonic cross section describing what happens during hadron, this hard collision, and it should be addressed by some zigzag dynamics, which is responsible for this long distance behavior. And so kind of what really the goal is to try to understand this factorization and try to kind of develop perturbative description, high energy expansion for this theory based on this factorization. Well, apart from there, let me just say that it's instructive to compare what to this expected form. To one interesting example, which is that's something which is known under the name TT bar deformation now, which is the same as flat space JT gravity. It's a statement that if for an arbitrary quantum theory in 2 dimensions, you can dress it with a phase like this at the level of S matrix and get dress theory, which I said, well, it has description in terms of TT bar deformation, and also it is indeed gravitational theory. And actually, the properties of the theory there have lots of similarities with what one wants, because it's dressing, it doesn't introduce any new non-elasticities, but it exactly introduces the time delays which match what one expects from the zigzag. Although the physics is different, because if one looks at this picture of the zigzag picture, it's clear these 2 quarks, they have different flavor, for instance. If these are some adjoint quarks which have different flavor, then the scattering here is a total reflection, while the effect of this TT bar dressing, it's always total transmission. It doesn't introduce reflection. So in details, that's a different class of theories, but we're looking for something like that, which would match the description of the Wolfschild theory. Okay, so now to make things more calculable, I will make advantage of the fact that Wolfschild theory lives in the 2 dimensions independently of dimensionality of the targets of the gauge theory lives. So one may hope that going to lower dimensional models, which are more analytically tractable, one may still get some insight in what happens here. So I will go all the way to 2 dimensions, because in 2 dimensions, pure glue is a boring series. There are no local degrees of freedom. So that's why the model which I will consider, it's 2D adjoint QCD. So there is Yang-Mills part, and there is massive adjoint fermion. In this case, it's just single Majorana flavor, but it doesn't really matter. And this model is perturbative in the heavy mass regime when the mass is larger than the string tension, which is set by Toft coupling. Yeah. No. I start with 2D QCD, and I want to study Wolfschild dynamics in 2D QCD. I take that Wolfschild theory in this gauge theory. So instead of talking about 4D pure glue, I start with 2D adjoint QCD. No, I'm not assuming. No, the goal is to derive Wolfschild theory starting from this gauge theory. That's kind. No, it's 2D Wolfschild theory in 2D gauge theory. So it's everything is in 2D. Gauge theory is in 2D, and Wolfschild is in 2D. So indeed, one may be puzzled. I think that's question reflecting kind of these confusions and what. Yeah, that's one way to say it. Yeah. What is the Wolfschild theory to talk about here? And to answer this question, it's good to recall how one studies Wolfschild theory at high dimensions on the lattice. What one does there, one looks at on the lattice, one looks at the 2-point function of Polyakov loops, and then one doesn't need to look at the straight Polyakov loops. One may introduce some wiggles on these Polyakov loops, and from there one extracts the finite volume spectrum of the string excitations. So one can follow the same strategy in 2D. One can look at the 2-point function of Polyakov loops. Of course, if it's pure Yang-Mills, because there are no transverse direction, I cannot put any wiggles there. So there is not much dynamics. But I have adjoint fermions. So in the presence of adjoint fermions, instead of transverse excitations, I may put these insertions of fermions inside. So what I'm doing, I'm studying this subsector of theory, which is created by operators with Polyakov loop wrapped around. If I put it on a circle, I wrap a Polyakov loop around a circle, and I start a single trace subsector of a theory, which obtained by making arbitrary insertions inside there, and that sector decouples from the rest of the theory in the planar limit. So that's what I call Wolfschild theory. Yes. Yeah. So this way I got local excitations on the Wolfschild, right? Yes. It's very interesting because it tells us that's very interesting point, because at this point this guy becomes a Galstina. So that's the point where it tells that this theory becomes massless. But that's not the point which I can study perturbatively. Yeah.
value breaks the wall sheet.
Oh, sorry. No, for general mass, there's no supersymmetry here.
General mass, there is no, but now that the on the wall sheet will emerge. What I'm saying is that there is always some progress to store this. That's what I suggested. Not only bosonic,
but in the advantage of this setup that at large mass, I know what to do. Let me show you. So I don't need to make any assumptions about wall sheet theory. I can just derive it from gauge theory, and that's what I'm going to do. And yes. No, for my purpose, it's not important. Just technically, my Rane fermion is the simplest theory. It's finite, and like it's just easier to study. But from the point of view of the story I'm telling you, it's not important. For other purposes like this supersymmetry, of course, it is very important. Yeah, it is important, but not for this story. Okay, so as I said, one can derive this Hamiltonian, describe wall sheet Hamiltonian, and that's basically the derivation is the superposition of two papers from 70s by Coleman, where he did this calculation for massive Schwinger model, and by Witten paper about discrete theta angles, as Zohar mentioned. So yeah, so okay, one way, well, there are several ways to think about wall sheet theory. One way, physical way, which is already mentioned, is to introduce non-dynamical quark, fundamental quark anti-quark pair and separate them very far apart, which corresponds to, which means I'm studying now my theory in the background of constant chromoelectric field, and equivalently, I might say that one studies this theory in the presence of discrete theta angle, but physically it's just this. I'm thinking in these terms. So I introduce this pair, then one fixes the spatial gauge, Ax equal to 0. A0 is non-dynamical, it's a Gauss's law, so one integrates it out, and one gets Hamiltonian, effective Hamiltonian for fermions. So there are fermions here, and in addition, well, there is this T and T bars. These are quantum mechanical operators describing spins of the quarks. So even in the infinite mass limit, quarks positions are not dynamical, but their color spins still dynamical. So these are really in this Hamiltonian, these are quantum mechanical operators. So in other words, the Hilbert space where this Hamiltonian acts is the tensor product of Hilbert space of free fermions times fundamental anti-fundamental fermions living at the endpoints. But the physical states on this Hilbert space they're determined by the condition that they should be have no color charge, so they should be color singlets. So the first step, and I'm working in the limit as I said when the mass is large, so this Hamiltonian can be studied perturbatively. So the first step then is to do the kinematics to characterize these singlet states. That's a mass. No, those taken to infinity. Those are strictly non-dynamical. So it's a mass of this fermion. Right. Yeah. Well, that's the full Hamiltonian is the sum of the free fermions plus this. So this is the part of the Hamiltonian which comes from integration of the gauge field. I didn't write the free. Yeah. No. Well, they're relativistic. They're just massive. I have free massive fermions with mass much larger than the string tension, and I have this interaction between them, which comes from F minus squared from integrating out. Yeah, of course. Yeah, my fermions are relativistic fermions. I just work in the limit where their mass is much heavier than the string tension. The number is not conserved, but no, not exponential. It's power law. It has heavy mass. Yeah. Right. No, but I can collide them at high energies. I can take them relativistic. They're heavy, but I can take them very relativistic and produce. So. No, it matters for this Hamiltonian. It matters that they're heavy compared to string tension. Otherwise, I cannot do this perturbative expansion. But right, so. Well, no. M should be large compared to string tension. Right. Well, this is exact, but if you were to do perturbative calculations, you need to go to energies well above the string tension, where theory becomes free. And right, so in particular, if you want to be perturbative at the scale of the mass of these fermions, they should be heavier. So, as for instance, one thing which happens at some, as was already mentioned, at some weird value of this mass, m squared equals g squared n over pi, something like that. These fermions actually on the wall sheet they're massless. Yeah. Well, it remains what? It's not a straight line. No. No, that's it. Wait, Misha. It's in 2D. But wait, well, there is a reason I call this zigzag, right? So that's why zigzags will, right? No, there are no transverse direction. But you are right. The string will oscillate. Yeah. So you'll see momentarily. That's the whole point, right? So, but let's be first do kinematics, right? So there is a ground state, which is just spin singlet, where these two spins at the end of the wall they're untangled with each other and form polar singlet. Then there is what Witten in his paper called free quark. Well, it's just quark inserted inside of the string, and it's free because it can move. It's not confined. Well, it can move everywhere. But of course, it's not free. There is, if I look at the level of two particle states, then I have states like this. But this is double trace state. These are mesons, which exactly that's what decouples from the dynamics I'm interested in. But in addition, there are states like this. So there are two particle states of this form, and this is what I want to collide. So I want to consider what happens as a result of the collision of these two particle states. Now there is something very interesting happened here. Namely, if I look at these two particle states, well, actually, because of the color ordering, there are too many states for a pair of identical particles. I'm talking about single flavor. And so in particular, if I take a, say, tensor product, a scalar product of two states like this, that's the answer. I don't get the exchange exchange term. Right, yeah. So, and of course, one can go to n particle subsector. So in n particle subsector, one gets color singlet states like that. And again, they have the scalar products between these states of this form. So this is an example of a theory with infinite, what's called infinite quantum Boltzmann statistics. So it's a counterexample to the statement you may see in Weinberg's book that if you do quantum field, relativistic quantum field theory, it happens in the Fock space. So here Hamiltonian naturally acts not in the Fock space, but in this weird space of this infinite Boltzmann statistics because of the color ordering, because I took planar limit. So, because that was kinematics. Now, to do dynamics, I need now to look at the Hamiltonian. And so, particular, the Hamiltonian is a two-particle sector. It looks, well, it roughly takes this form, where this U factor is some function of the momenta, which is basically almost one everywhere. It's kind of, it has some, well, it's some non-trivial function, but it's smooth and everywhere close away from the string scale, QCD scale. It's for the one. So if I set it to one, then I'll get Hamiltonian. If I then go to real space instead of physical space, and I get Hamiltonian of this form, which tells me exactly what Misha already said. So this works. So when the color ordering in space is the same as the space ordering in space, then there is no potential. But then as two particles collide, they may overshoot, and the string is getting stretched. but then they eventually got reversed back. But it tells me that, well, actually, at the level of on-shell states, because this potential, it kills half of the asymptotic states. So at the level of on-shell states, I restored usual Fock space. But at the level of off-shell dynamics, it happens in this weird Boltzmann space. And so it's interesting. It's a way to get a long time delay without having any resonances. Usually the common law kind of when you have scattering and you have a resonance, we have long time delay. That means there is some narrow resonance. So that's a very different mechanism and kind of related to some non-locality of this theory. So there is a kind of large region of space being formed. And that's, we're coming back to this picture. So this potential exactly describes what happens here. Kind of zigzags, they restore much of this dynamics, which naively is not there because I don't have transverse dimension, but they restore much of the geometric dynamics. Okay, how I'm doing on time? 15 minutes. Okay, then I'll try to go very fast through the classical story, even though I love it. But so, yeah, so okay, what we're trying to do, so there was this complicated Hamiltonian describing worldsheet dynamics. We want to develop perturbation theory. And so it's natural then to take as a starting point, so set that function u to 1 and look at this as a starting point. And in particular, in kind of in this approximation, all the at high energies, also the processes with Parton number non-conservations are suppressed. So my leading Hamiltonian, it's diagonal in terms of the number of partons, but at each number of partons I get in this theory. And it's straightforward to check that, first of all, this theory is, it's Poincare invariant at the level of classical Poisson brackets. And this is something interesting because we often hear that kind of the fact that doing quantum field theory, it's a consequence of trying to combine quantum mechanics and special relativity. Well, actually, it's wrong. Well, it's correct, but the statement, we don't need quantum mechanics. If we want to do special relativity and Hamiltonian dynamics, then there is a statement back from 60s, which says that essentially you cannot do it in finite dimensional phase space. So you have finite dimensional relativistic theory, then it's equivalent it's just a theory of free particles. But this theorem holds in dimensions higher than 2, and this model is counterexample. So this is a really instance of doing relativistic physics in finite dimensional phase space, which I think on its own is interesting. It's related to these exotic statistics which one gets here. And furthermore, it turns out that it's integrable in the massless limit, and which is a good property for me because we wanted to use this model as a starting point for perturbative expansion. So it's better that we have a solvable theory as our zero-zero approximation. So this is what. So finally, like 10 minutes before the end of my talk, I finally defined for you what zigzag model is. So it's a theory with this embarrassingly simple Hamiltonian. So it's a massless limit of what I wrote before. So as I told you, it's Poincare invariant. So that's explicit expression of the tensor charge. This is the boost generator. And yeah, I think I should skip, if I want to describe quantization, I should skip the, so as I told you, the theory is classically integrable, and that's kind of how scattering goes in this theory. And integrability just means that the set of momenta, initial momenta and final momenta is exactly the same. And there is a very nice construction of this integrals of motion, and this integrable structure, it is super nice. But I'm going to skip it. I'll just give you a summary here. So the summary is that it's not only integrable, it's what's called maximally superintegrable. Namely, there are 2n-1 algebraically independent conserved charges here. So n of them are in involution, is the maximum number of charges in involution, but the total number of dependent charges is 2n-1. And actually, well, these charges, they provide the map of this theory into a system. It's a fixed number of right movers and left movers. It provides a system of just massless right movers and left movers. So it's these charges can be sort of action angle variables mapping these dynamics into dynamics of just free massless particles. And as often the case in these maximally integrable series, I can calculate, say, classical time delay, and it reproduces, it's equal to this. So time delay is proportional to collision energy, essentially, which is obvious from this zigzag picture. And that's exactly the same time delay, which corresponds to TT bar phase shift, which I already. So far, we're doing classical, right? But it just, this time delay would correspond to this phase shift. Yeah, if there is a phase shift, yeah, then it should be of this form to reproduce this time delay, exactly. But here is just a classical time delay, which one gets in this mode. Well, because it's interesting. Because it's integrable model, and I wanted to use that Hamiltonian as zero-zone approximation for some perturbation theory. So I wanted to get yes. Yeah, of course, no, can consider two. Yeah, but the statement is that at any number of partons, this theory is integrable. What? Well, but I can put 10 partons on my string, right? And okay, let's start with 2. And indeed, kind of my next slide, all quantization will be done in 2 particle subsectors. So yeah, so if you don't want to think about more than 2, you should be happy for the remainder of this talk. It will be about two particles. So let's try to quantize it. So what kind of our wish list expectations? First, we need to keep Poincare symmetry because again, we want to use a starting point for perturbation theory. We want to keep integrability, even though at the level of 2 particle subsectors, that's not a very meaningful statement. And we kind of expect that the classical phase shift actually stand and change upon quantization, because while this TT bar deformed theories in many descriptions, they are 1 loop exact. So given that at the classical level here, I have time delay which corresponds to phase shift of exact quantum theory, one would expect that if I quantize it consistent with integrability, that the phase shift won't change. But well, I mean that I meant that the phase shift which I get in the quantum theory, which will exactly reproduce classical time delay with no corrections. That's the expectation. But the first 2 properties are really a must, and this last one is more like expectation. Okay, so as Misha suggested, let's just look at the 2 particles sector, and let's first try to, well, it's very embarrassingly simple Hamiltonian. So let's quantize it just in a naive way, impose Q and P, canonical commutation relations. Well, there is this absolute value operator which appears here, but it's not a big deal. We know how to define it in the momentum space. So that results in the following Schrodinger equation. Well, I meant the K, it gets convoluted. Well, it's K is the same as Q prime here, I guess. Well, no. Yeah, no, I probably was. Well, this is this K is P, sorry. Yeah, this K is P, right? Yeah. And but this is really the formula, right? This is, yeah. Yeah, this K, yeah, this formula K is P, right? Yeah. You're right. Okay, so this is the naive Schrodinger equation which one gets for this system. So first of all, but one immediately notice that there are several kind of strange things about it. So first of all, kind of this theory, this 2 particle sector, it's already has 3 subsectors, right? In the classical level, I have 2 possibilities. I have 2 left movers and they never talk to each other. I have 2 right movers, they never talk to each other, and I have left-right subsector. And with this quantization, the structure is completely lost. It's immediately, well, it's easy to see there are no wave functions which correspond to 2 left movers, which kind of stay on one side or the other. It's incompatible with uncertainty principle. So I lose this. One can calculate phase shift numerically, and what's shown here, this red dots are numerical result, and blue is what I call classical phase shift, the TT bar phase shift. And one sees that, well, in the large momenta they agree, but at low momenta they disagree. And finally, one can check the quantum level with this quantization. The Poincare algebra is spoiled by some nasty contact terms, and it doesn't look like there is a normal ordering prescription which would restore it. So that's not the quantization which we want.
But actually, go back to that slide and show the first pair exactly like the top.
Well, Toft equation is different because here it's from minus infinity to infinity. Toft equation, it's on the finite thing. It's 5, yeah, right. Well, it's this model is close. What? Right. Well, this model is similar to Toft, and we'll see actually it will be the correct equation is more similar to Toft. Yeah, but this is just Fourier transform as a momentum of absolute value, right? So, well, Toft again, it's on the finite interval, and so it's not exactly Toft. But so, well, there is this problem with quantization. It's good to try to understand where these problems are coming from, and for that, it's good to look back at the classical phase space of the model. And so, what here I went to the coordinates kind of where I separated. I'm not good in drawing 4-dimensional spaces, so I separated total momentum and center of mass motion, and I'm drawing kind of slices of this space at a finite value of the total momentum. So that's for negative value of total momentum, that's for 0, and that for positive. And these are the phase space trajectories. So as I said, there are three different subsectors at the already classical level: left mover, right mover, and left. And so one sees that already at the classical level, this Hamiltonian flow, it's kind of badly discontinuous due to these absolute values appearing in the Hamiltonian. It's badly discontinuous at the boundaries of the phase space. So that tells me that's the right thing to do. So really, my phase space is not R4, which I was naively assuming during this classical quantization, but really it's R4 without this boundary. So in other words, one should really quantize separately this theory in these different regions, thank you, of the phase space, and they have non-trivial geometry. It's not just R4, and naive quantization completely ignores it, and that's the reason why that doesn't get physics right. So one should do quantization which kind of cares about this. And well, left and right sectors are kind of trivial. You have just non-interacting particles there. So let's discuss how to quantize the sector which describes. Well, really my phase space. Well, I should cut out these regions from the phase space, right? Yeah. Or again, it's better to think that really there are 3 different sectors, and the interacting sector it has this form, well, which is simplexically it's equivalent to a half plane, right? Because kind of this region can be simplexically mapped to each fixed value of p. It can be mapped to a half plane. And so what we should do quantization in the variables which kind of which know about this structure. And indeed, so well, as I said, there is a classical analysis of this theory which constructs action angle variables, and these action angle variables actually define, they're globally defined action angle variables in each of these subsectors. So in particular, in this left-right subsector, well, they map if I map from initial variables, they map to total p and conjugate variable, and total h and the conjugate variable. So it's a phase space of 2 massless particles, one left mover and one right mover. So now in these new variables, quantization is trivial, of course. I do it in the momentum space. I get the states labeled by momentum and energy. So that's my phase space. And I get just massless free particles. But to reconstruct the real space dynamics, to calculate the S matrix, I need to come back to initial variables. So these are rather scary looking formulas expressing initial physical coordinates in terms of these canonical variables. And to calculate S matrix, I need to work in the initial coordinates. It looks a bit scary, but let's go to p equal to 0. So if p equals to 0, formulas simplify a lot. So I have a state labeled by energy, which is positive. There is a canonical coordinate operator conjugate to this energy, which is just equal by derivative. But because h is positive, actually, well, this operator is well known. On the half line, momentum doesn't admit self-adjoint extension. So on its own, that's not a good operator. But the operator which I care about, it's this one. It's a physical coordinate. It's given by this expression. And here it's a little bit of ambiguity how one defines absolute value of Q for operator Q on the half line. And here I basically followed essentially what Tov did on an interval. So I use the same formula. Well, there is some motivation for doing that, but let's just take it as a prescription. So we define this absolute value of Q by the same formula which we're using on that full line, but integrate from 0 to infinity instead of from minus infinity to infinity. Well, and one can check that this operator actually is self-adjoint. So at least it's a nice operator to use. Okay, so after we've done that, so then we need, now we have everything to solve the scattering problem. So to solve the scattering problem, well, usually we solve this stationary Schrödinger equation, meaning we want to determine this quantity, the stationary scattering wave function. And here it's given as a solution by what I call Q Schrödinger equation. It looks a lot like Schrödinger equation, but the catch is that I'm working the energy eigenbasis. So usually we work in the coordinate representation and we look for energy eigenstates. Here in my quantization, I ended up directly in the energy eigenbasis, but I need to look for coordinate eigenstates. But of course, for the purpose of calculating these matrix elements, both approaches are equivalent. So I need to solve this equation. But what the nice thing in working in this representation is that for scattering problem, I'm interested in the Q to minus infinity limit, which is a asymptotic regime here, which automatically, if one thinks about this as a kind of normal Schrödinger equation, the Q playing the role of energy, it automatically takes me in semi-classical regime. Even though it's not an approximation, it's just for the purpose of to determine S matrix is this language, I am automatically need to be solving semi-classical approximation. So, well, I skip the details. I'll just say, well, it's rather straightforward. Well, there is leading order. It's rather straightforward to find the form of the wave function up to prefactor. So the leading exponent is trivial to find. To find the prefactor, one needs to match the solution to what happens at h equal to 0. And fortunately, the equation which one gets this way is actually was studied before back in 79 and later was revisited by Fatyev, Lukyanov, Zamolodchikov. So this equation arises in the semi-classical expansion of the Hopf model, actually. Well, which is not surprising. It's essentially, well, it describes what happens in the Hopf model close to the turning point. So it's not surprising that I'm getting the same equation. So there is a solution, exact solution to this equation given by some Mellon transform of the double sign function. But in the asymptotic regime we're interested, it has very simple form. So at the end of the day, when one combines things together, one gets this answer for the wave function. So the scattering phase shift, it's exactly what one would expect from TT bar, but there is extra constant correction, which doesn't affect time delay, but it affects if I want to put the system some finite volume. Well, it affects some quantities, but it's mostly really the TT bar phase shift. Well, and kind of we checked, there are some interesting subtleties there, but just to make sure, as I said, this quantization looks manifestly Lorentz invariant before, well, at the level of Hilbert space, but then I introduce this physical coordinates which look really weird. So it is as a cross check, we did repeat that as a calculation at finite momentum and reproduced again the Lorentz invariant S matrix from here. So yeah, so I'm about to finish and end with conclusion remarks. So first of all, well, the same strategy, of course, essentially the strategy here is quantization using action angle variables, which provide globally well-defined parameterization for the my phase space here. So it works for any n and preserves integrability more or less by construction. So in that sense, it achieves what I wanted. There is kind of a number of fascinating subtleties which I didn't have time to tell you about. In particular, like this at finite p, the form of the scattering wave function is somewhat weird because physical coordinates with these prescriptions are not, the commutation relations are not canonical. So in some sense, it's a non-commutative theory, but which is clear from the fact I started initially to do canonical quantization in physical coordinates and failed. So now I did quantization in different coordinates, but the price to pay that what I call physical coordinates, they don't have canonical commutation relations, which reflects that the theory is somewhat non-local. Finally, I should say, well, we managed to quantize the model, but so far I didn't have a chance to tell you about the classical story. But I should say that classical story is much nicer and much more elegant than the quantum one. And in particular, this so far, well, this wave quantizing, it looks a bit scary as a starting point for perturbative expansion. This sorry? No, I work at the ultra-relativistic limit, but I work at the leading order in the perturbative expansion. So I take the order of limits I'm taking the order of limits kind of energy much larger than m squared, much larger than g squared n. And in this regime, all non-diagonal terms with parton production, they're suppressed just because theory is free in the UV, apart from this, this scattering. So I work in this regime. So that's for the purpose of high energy expansion, this Hamiltonian really a natural starting point to develop it. But the challenge is that, yeah, okay, we have a solution of the quantum problem with this Hamiltonian, but it looks like a rather challenging starting point to do perturbation theory around. So you mean we talk about the spectrum of hadrons, right? Right. No, what do you mean bosonic? So here I was just, huh? No, but all the states are color singlets. So what you call bosonic and fermionic, those are states. That depends on what n, right? So if so here they're just determined by the number of partons. So in the kind of it's even worse. Yeah, I have both. I just right. Yeah. Yes, Zohar. No, but that's a different because I'm not. That's a kind of that study that's a spectrum of strings like this, and here I'm studying the infinite long string and studying scattering on that. Right. So it's interesting question, kind of how these two problems are related. So, but well, but. Oh, no, of course, no. It's the next order in G squared. So that's kind of what one wants to do. One wants to start with this zeros order approximation and start doing perturbative expansion G squared n, which in particular starts immediately with. Well, it's first of all, here the quarks are it's heavy quarks in the regime we're working in. Well, we have some preliminary results of that. At least, like, I don't think there is a naive lunar radiation doesn't work here. And it's not that one getting lunar radiation. But definitely, there are terms in the full Hamiltonian. We have explicit expression for the full Hamiltonian, and there are terms which we dropped, which are small in this limit, but they mix stack sectors with different number of partons. So that's the challenge: how to start doing perturbative expansion with this Hamiltonian. Start with this zeros order approximation. That's kind of the next step, which looks quite challenging, but that's.
Thanks, Sergei, again.
I want to say,
We have one more talk.
one more talk.
Well, not right now, but after coffee, right? So after Mohammed's talk, so we should start again at 4. So. If you're going there now, yes. Starting at the hotel. Are you starting at the hotel or? Yes, you take the green line, the same way you do it. And the US taxation switch rates on blue. Go forward. And isometric type of determinant no, no. So far. Three angles for a simply say, how do you and isometric? Yes, very similar. That's true. So, yeah, exactly. That I claim you know. Yeah, yeah. It's stuff that. This, of course, works. This one is on up the line. Bring down the fundamental violate one point of group. Special in the whole falls apart. That makes sense. Once they equal the boundaries, hopefully somehow it's something, yeah. Breaking the balance. Yeah. Both of them are very level here.
So these differ by
But if you really want to do that, this people, or generic representation, or for example, influence. There is a regime that tension between close to zero. For a generic representation, so something like that. So, but to get this formula, you have to establish 3 and 1.
plus, and kind of that's not quite right.
Just comparing these two.
But even that, I mean, it's here, this correction to just cause some power.
Yeah, it's correct.
Right.
But on the other hand, this cognitive dependence does not feel very reasonable. They see only a 5 difference between this game and this. It's 7. Vector 7. So the 5 vector 5.
Right. Whereas Lorraine
Again, is very pathetic. So get something vector 5, this has to be 10 to the 5. 10 to the 50, I am sorry.
But you even strong up when you do it, but well.
Yeah, nothing very yeah. So normally this is correct. The large end is for that and not create it seems to be fake.
Well, I don't trust the
I think this is, I don't know. I did it with some functional math, but yeah.
I'll bet it's that.
Maybe there is some dynamic
color. It doesn't. This is an asymptotic formula.
Oh,
Maybe you're really unlucky when you actually become useful because of the
oh, figure out. Yeah. Because it's figure in the system.
yeah, I mean, in terms of looking at what's actually been done with plastic subtensions,
Right, right. Yeah.
but
So what I learned from you is that Bir Z is like Ber Zeit, and that Anber is like in Bar. See, there is one-to-one correspondence. Anber is in bar. It's this stone, which is a bit of a, yeah, of course you know. But what I'm saying is that just to make sure that the translation is this color orange, right?
Right.
It's so in Israel, the word in bar, like Anber, is common for a name for girls. First name for girls.
Is the same here in the US, Amber, right?
Yeah, I guess. Anber is like, I see. So they call you sometimes Anber by mistake.
No, actually, no. Because
That-
it's
that-
N.
Yeah, but do they notice?
No, I
They
don't
don't make
think so.
confusion.
No, I don't think so.
So it all descends from Hebrew and Arabic, whatever, some Semitic languages.
I'm not sure actually Amber is Semitic at all.
Yeah, it has to be both. If it exists in both languages, it means that the root is old. It was not brought from either language, unless it came from either Farsi or Turkish, Greek. Maybe could be. We can check.
No, not the light portion.
I told you about my Egyptian genetics.
You told me yes.
But that was long time ago, like 15 months,
Right.
which didn't leave any, in my appearance, nothing whatsoever. Well, it's obvious that my ancestors mixed with Eastern European people. That's obvious. I don't look Semitic, right? No Zohar.
Almost everything except. Yeah. I can read.
No mission. In your appearance, you don't look Semitic. Have you ever, did you do this genetic exam ever? Yes. What did you find?
Yeah.
If I may ask about your ancestors, do they descend from Israel or from Kazakh? No, because there was a kingdom of Kazakh that was very.
Okay.
No,
Surviving.
on the paternal side, it's mostly Ashkenazi Jew. What's that?
Yes.
With some,
Yeah. Okay.
some mixture
It's
of Israeli Jews, but a very special type. That's also very common. One Ashkenazi Jew, but only Levites.
Goyim or Levites?
Yeah.
I'm asking Goyim or Levites? Because the Goyim,
Levites.
you know why? Because the Goyim is there. So if the father is Goyim, the son is Goyim. And then it's like easy. The Goyim goes forth. So, but your shoe it was Levi, so Levi is not paternal. So it's not distinct. You cannot trace it. Maybe it's Goyim. I have the point gene as well.
More or less.
But 15,000 years ago, they told me this genetic. No, they said the Y chromosome is from Egypt. The Y chromosome, you can trace long ago, because under those mutations very rare. So the quanta is 1,000. So they could tell me what, like the most distance was 15,000. And then it was, and then later it was like Iraq area, and then Israel area, and then, but it was kind of even close to the biblical story, and then the rest was really much history, like 2,000 years ago from Israel, Turkey, then Italy, and that's it. Now, we didn't know anything about it. It was the last trace that the next one.
Oh, but that's very common. I can say from Africa, go and then go East Mediterranean, and then up north.
Right. All people, there were very few exits from Africa. It was released. The Russians went. Like Europeans, left Africa.
Most of these are possible.
100,000 years. No, but my understanding, 15,000 5,000 years ago were 5,000 years ago. So I'm really from the middle. Although I don't do. I think actually my nose, I can there's a level. My nose is quite wide.
Exactly like you are like Pharaoh. You should have
No, but you see, my nose is more, my nose is wide. So it's more African, but that's the only thing in my appearance that I can say. For the rest, I'm Eastern European.
Well, in principle, so there was a bottle start with very
This is why.
was why there's unfortunately. Yeah, that's why
It's very dark.
It's okay, it's fine. I understand. It's okay.
You remember?
Yeah, good to see you as well. Have a safe trip.
Yes. Something that.
What is your thought?
25% before. Then the child will not survive the birth. So only 25% is fake. 25% not confessed, and 50% is a carrier like that. So it's still okay.
Oh, of course, my daughter, yeah.
But no, it's different.
Now
It's kind of it's a
Second
mix.
infection.
It's not for this.
Because I have the question.
Thanks. Then it's very close.
It's very close, yes. But his relatives are known for this. His grandmother died recently at the age of 102. And until the age of 101, she was totally self-sustaining. In good health, in absolutely good memory. I wish I had such
Where? Father. Now it's, and he's starting now his new book. He's still traveling just before the pandemic.
I'm very knackered, so I'm not sure
Decided
how we
not
follow it.
long.
Well, I pretty short.
Be prepared to tell
To the
me
US
over a
also,
beer
and then
again that this
You're gonna say. No, I understand because I'm gonna keep it pretty short. Because
Great.
3 years, it's not.
3 years, 3 days. That's
Does everything work?
I think so.
You know how this works, right? It's oven, right? Yeah. This integrability exception, Lorentz invariance is a particle number. Now that you say it, yes, but I never. In my classes, I always said, "Oh, particle number."
I was studying, I was studying you the small and
Well, I said that. Take her out. I know why so it's here. Variant. But if it was normally it's part of the production somehow. Well, but then just the same classical mechanics. The theory was doing so really, if you want to do interactive theory, you're going to want to right. All right, so it's time to get started. First thing I want to say is, before we leave this room, one thing that would massively help Alicia is if you brought in cups or bottles or other random stuff, if you could take it out and put it in the trash bins, that would be amazing. And then the other thing is, please don't run away immediately after Mohammed's talk. Alicia wants to say a few words, about 5 minutes. Yeah, maybe less. Okay, so our last but by no means least speaker is Mohamed, who's going to give us a wonderful talk about twisting and nonperturbative phenomena.
Thank you. Thanks a lot for the invitation. So because I know it is extremely late and everybody is tired, so I will try my best to keep it really short. And I will tell you about twisting and non-perturbative phenomena. And my talk will be based on this collection of papers with Eric Poppets, Minho Sun, and Sango Hong. So let me start with an overview about what I would like to tell you about. So I will be talking about non-perturbative phenomena. And we know that the non-perturbative phenomena are ubiquitous in physics, and they appear in many different applications, from confinement in Young-Mills theory, condensates in QCD. Also, if you would like to understand the domain wall physics in Young-Mills theory, you will need to understand non-perturbative phenomena, and also the baryon number violation in the standard model, and beyond. All these different phenomena amount to understanding the non-perturbative dynamics. And we all know that in order to understand this non-perturbative phenomena, we need methods beyond Feynman diagrams. And for that, subtle understanding of topology of gauge fields and manifold is mandatory. Recently, there has been a revive of old concepts in the light of new understanding, and this actually gave us many interesting new observations. So nowadays, we all hear words like twist, fraction, topological charge, 8-Hopf anomalies, one-form symmetries, topological quantum field theory, etc. And they are all now important for the understanding of these various non-perturbative phenomena. Today, my talk will be really about what we call 8-Hopf twists. And I will be using 8-Hopf twists in two contexts. First of all, I'm going to use them as backgrounds. And it turns out that when I turn on 8-Hopf twist background, this can give rise to generalized 8-Hopf anomalies. And the other context or the application I'm going to talk about rather briefly in this talk is when we sum over this twist, 8-Hopf twist. So in this case, we sum over gauge bundles of 8-Hopf twists, and this will give rise to violation of global symmetries. So let me start with the first part, which is about the generalized 't-Hooft anomalies. So we all know that an 't-Hooft anomaly is in fact an obstruction to gauging a global symmetry. And what I mean by that is as follows. So you have some global symmetry, you introduce a background gauge field of the global symmetry, and then you examine what happens to the partition function under a gauge transformation of this global symmetry. And if the partition function fails to be gauge invariant, we say that we have an 't-Hooft anomaly, which shows up as a phase e to the I gamma under this transformation. And of course, they are of paramount importance because they are RG invariant, and hence they can be used for the UVIR matching. What does this mean is that we can actually consider some strongly coupled theory, which is presumably asymptotically free in the UV, where we can compute this e to the I gamma factor exactly. Then we flow to the IR. The theory becomes strongly coupled. We don't know how to solve it. However, you can propose scenarios, but whatever scenario you propose, it has exactly to give you this phase. Otherwise, you can get rid of it. I don't know what is this problem, but I have to keep just doing this all the time. Sorry for that. Not really. So you think if I connect to the blog, it's going to be better? All right, I can do that. Thank you. So as I mentioned that whatever scenario you propose, it has to exactly give this e to the I gamma phase. Otherwise, you have to get rid of the scenario. And it turns out that whenever we have an 't-Hooft anomaly, then your theory cannot be trivially gapped, which means that a unique gapped vacuum is excluded in a theory with 't-Hooft anomaly. So you have to have multiple vacua or some massless modes in order to match the anomaly. So these anomalies were discovered by the 80s, as the name suggests, by 't-Hooft. And today we can call them the anomalies of zero form symmetries. Sometimes I will call them ordinary 't-Hooft anomaly or all the 't-Hooft anomalies. Okay, it's up to you. Okay, you can pick your favorite name. The important thing about these anomalies really that were discovered back in the 80s that these are anomalies of a zero form symmetry, or what we mean by that, we mean symmetries that act on local fields. The very famous example is the anomaly of the SUN flavor. So if you want to gauge it, you need to introduce one form background gauge field, and this gives rise to a topological charge, but this topological charge is always an integer. So this actually what designates this kind of all the 't-Hooft anomalies. 't-Hooft also introduced what we call 't-Hooft twists. These actually are fractional fluxes, but what role they could play in 't-Hooft anomalies were not understood until recently. So in 2014, this group of gentlemen actually generalized the notion of a global symmetry to a higher form symmetry. So instead of talking only about a zero form symmetry, we can talk about one form symmetry, one form global symmetry, which acts on one-dimensional objects. And in this case, we are talking about Wilson lines. The very famous example is the ZN1 form center symmetry of SUN Bure-Yang-Mills theory that acts on these Wilson lines. It turns out that if you want to introduce a background gauge field of this one form symmetry, here I'm saying gauging, but really what I mean at this level, introducing the background gauge field of this one form symmetry. So if you do that, then this will give rise to a two form gauge field, B2. And now it turns out that this B2 sources a fractional flux on two cycles of some four-dimensional manifold M4. So if you take this B2 and you integrate it over these two cycles M2, you will get the fractional flux, and this is what we call the 't-Hooft twist. You can also take this B2 and you integrate it over M4 and use this expression, and this will give you Q, the topological charge. And the new thing here that this topological charge is fractional. So these are the background gauge fields of this one-form symmetry. You can also try to couple this B2 to Young-Mills theory via some kind of topological quantum field theory called BF theory. And using this construction, you can discover new 't-Hooft anomaly, as was found by this group in 2017. So one very famous example, and one of the first examples, is that if you take pure Young-Mills theory, you take, for example, SU2 at theta equal to pi. This theory enjoys the T symmetry times invariant T symmetry, and okay. And if you try to turn on a background gauge field of the one-form symmetry, you find a mixed anomaly between the T symmetry, which I denoted here by Z sub 2, 0, which actually emphasizes this is a zero-form symmetry. So I find this mixed anomaly of Z2 in the background of the one-form center symmetry. And because of this anomaly, in order to match the anomaly in the IR, one of the scenarios is that this T symmetry has to be broken. So in other words, that as you actually go from theta equal to 0 to theta equal to 2 pi, you should expect some kind of a phase transition at theta equal to pi. So this is the first example of this kind of anomalies, but then some question, one general problem that appears is the following. Consider a quantum field theory that is endowed with fermions and some symmetry G. What is the maximal set of anomalies that your theory could have? And this is a highly non-trivial question, and I don't think that we even near to answer it completely. But today I would like to just give you some show you some method that enable you to find a large set of these new 't-Hooft anomalies. And more anomalies you can have, the better, because the tighter the constraints you can actually put on your strongly coupled field theory, so you can actually eliminate so many scenarios. But before telling you actually how we are going to find this set of anomalies, I have one first task, which is as follows. Let us start with some four-dimensional manifold. By the way, okay, all the anomalies I will be talking about today are anomalies in 4 dimensions, okay? So given some four-dimensional manifold M4, the question is, what is the how to turn on the most general background fluxes of this G? So let us remember that our quantum field theory, okay, enjoys some symmetry G, and the question that I'm trying to answer is how to turn on the most general background fluxes of G. And here in particular, I will be interested in discrete fluxes because these discrete fluxes are going to give me these new anomalies. So this brings us to a way to find these general fluxes, which is called the compatibility condition. So what is that? Just allow me to be a little bit abstract for one slide, and then I will just turn on to some specific examples, and I will show you how these new anomalies actually can constrain our strong dynamics. So let us consider some four-dimensional manifold M4 that is covered with an atlas of charts U sub I. Also, let us assume that you are putting some fermion chi on your manifold. For practical purposes, you can think of chi as, for example, a Weyl fermion. Now your chi that live on the chart U sub I is denoted by chi sub I. And if you want to describe the exact same fermion on the chart Uj, you use chi j. But then you ask yourself, okay, what about the intersection between Ui and Uj? How am I going to go between chi I and chi j? And the answer is that you need to use what is called transition functions. These are the transition functions K sub ij, which are valued in some representation R of your symmetry G. So this is how you go between Ui and Uj, but this is not enough. What you actually need to do is that on the triple overlap between Ui, Uj, Uk, you have to satisfy this cocycle condition that this multiplication has to give 1. This is the compatibility condition I am talking about. And if you can make sure that this compatibility condition is obeyed on your manifold, then you are able to turn on these fluxes. Again, here I'm a bit abstract, but I will be very concrete in a minute. So let me give you a very specific example, okay? But before that, so it turns out that sometimes, depending on the representation R, we can relax this compatibility condition. I am really sorry for what is happening because this is very annoying. I bet there's some. Yeah, I think I have to like put my finger on here all the time. Okay, maybe this is what I should do. Okay, so the idea is that actually, yes, I mean, sometimes, and depending on R, we can relax this cocycle condition to this cocycle condition where K now lives in the fundamental. You see here, I replaced 1 by the center of the symmetry, Z of G. And if I can do that, then in fact, I can turn on the background field B2 of this center. So let me give you a very specific example. Let us take chi to be in the joint of SUN. In this case, I can replace this cocycle condition by this cocycle condition. Here you see that I have on the right-hand side there some Zn phases. Why I can do that is very simple. Because my adjoint fermion is represented by n boxes in the Young tableau. Every box transforms as the fundamental representation. And whenever we have a fundamental representation, we have e to the I 2 pi over n phase. And because we have n boxes, all these phases multiply together and they give me 1. So I am back to my original cocycle condition. So I will always play this game whenever I want to put any kind of fermion in any representation on some 4-dimensional manifold. You can think of it this way as well, right? This is another way of saying it, that you have some kind of, like in this example, SUN with ZN bundle, and you want to lift it to SUN bundle, but exactly, this is but here is actually the other way around. Here actually I can turn on some background fluxes which are discrete fluxes. That, for example, if my fermions were in the fundamental, I wouldn't do that easily. Okay, I have to work with. No, I mean unless I have U1 baryon, then I can do it.
So there is no center. How do you just back to your original? So you're only allowing yourself to introduce these fluxes because some of your G is fake.
Some of my, sorry?
Some of your group G is fake.
Yes, exactly. Right, I agree with you, okay? So my faithful, it turns out that my faithful symmetry might not be the G, it has to be actually G modded by something. And this is why actually I can turn on these fluxes. That is exactly the idea, yes. I'm actually going to mention that in some concrete examples. Yes, exactly. And the idea is how to determine this modding, and determining this modding can actually happen in different ways. And using the compatibility condition or cocycle condition is one of the ways. And to my flavor, actually, this is the easiest way. So I can solve some algebraic equations and I can find out the exact modding. Thank you for the questions. All right. So, however, why I am insisting on turning on these backgrounds on M4 if we know that the anomalies really are not sensitive to the manifold, but to the cohomology information. And it turns out that I can use the manifold in order to capture this cohomology information in a simple way. So, from now on, I'm going actually to be very concrete, and I'm going to play the following game. So I will take my theory to be given by the following group. It is SUN color cross SUN flavor cross U1 cross some discrete chiral symmetry. And I will take my manifold to be either T4, the 4 torus, or the CB2, the complex projective space. And by putting my theory on either of these two manifolds, I will discover new anomalies. So in order to do that, I am going actually to turn on fluxes along U1 and along the cartons of SUN color cross SUN flavor. So practically how I can do that, it is a very simple recipe. Okay, so these are the background fluxes that, that I want to turn on. These are the 8-Hooft fluxes. So they are given by this expression. L here is just the size of my torus, which it can be taken to be a symmetric torus. M1, 2 are just integer, and H are the Cartan generators, and nu are the fundamental weights. So I turn on these fluxes, and then you can also turn on a flux in the U1 direction, and this fluxes in the U1 direction takes the following form. It is little nc, which is the nullity of the fermion. I'm putting on my manifold divided by n capital NC, which is the color. So these are the 8-Hooft twists. Now, once I have these expressions, it becomes trivial to compute the QC, the topological charge of the color, and the QU, the topological charge of U1, which are given by these expressions here. Yes, please. Yes, in general, yeah. Yes, I'm going to actually mention that. So you can turn on a U1 background, and then you put it on CP2, yes. I heard that actually, I mean, at least perturbatively, this is the cohomology group that actually captured them. It's not true? Yeah, there might be more, of course, but at least, okay, the anomalies I'm talking about today, okay, I mean, they will be captured by this. Yeah, of course, I mean, to be more general, I could actually talk about the cobordism group. Yeah, but I don't want to do that. Yeah, of course, the cobordism group is bigger than that, but I don't want to do that. Okay, so this is the recipe. Now let's see actually specific examples, all right, of new anomalies that we discover this using this simple recipe. My first example, I'm going to talk about 3 examples. My first example is an SU8 Young-Mills theory with a single Dirac fermion. So you can think of it as 2 Weyl fermions. In the 2-index symmetric or in the 2-index anti-symmetric representation. The theory has U1 baryon symmetry, but actually this is not the faithful symmetry. The faithful symmetry is U1 baryon modded by Z4. And this is exactly okay, comes from the compatibility condition I just told you about. How do you discover it? It is very simple, really. So there are 2 phases you have to take care of. First of all, you can try to turn on the full center of SU8, which is the Z8, 2 pi over 8. But because our fermions are in the 2-index symmetric or anti-symmetric representation, you have to multiply by 2 because there are 2 boxes in the Young tableau. Mod n, of course. But this is actually a non-trivial phase, and you have to cancel the phase. And in order to do that, you have to turn on a Z4 subgroup of U1 baryon. It is trivial to see that this gives 1, and this explains why the modding is by Z4 in this case. So once now we have the compatibility condition obeyed on T4, I can just use the exact same method I told you about to compute QC and the QB. Then you turn on these backgrounds. and you perform a transformation by the discrete chiral symmetry, and you find that the phase that you acquire is a maximal phase. It is valued in Z10 or Z6. This is the maximal phase actually you could have in this theory. By the way, these kinds of anomalies are called CFU anomalies, which stands for color flavor U1 anomalies. Okay, and in general, they are mixed anomalies between the discrete chiral and these backgrounds, or between U1 and the discrete backgrounds. So let me show actually, okay, let me try to convince you that this is really, okay, the maximal anomaly, okay, that you could have in your theory. Let us try to compute other anomalies. Let us, for example, turn on the two-form center symmetry and apply a discrete chiral transformation. We find that actually the partition function doesn't transform. The phase here is trivial. So really, there is no anomaly between the discrete chiral symmetry and the Z2 one-form center in this theory. Another anomaly you might actually try to compute is the ordinary or the all-day-Hooft anomaly by turning on integer flux of the U1 baryon. And in this case, we find that the anomaly is valued in Z5 or in Z3, depending on whether the theory is in the two-index symmetric or anti-symmetric representation. And this phase still is actually smaller than the phase we get from this generalized CFU anomaly. Oh, for Z10 or Z6, yeah, depending on. Yeah, this is the cobordism anomaly that you are. Yes. Yeah. These are other anomalies that I'm not considering here. Yeah. Yes, yes, yeah.
It's not like you keep a particular, more like you keep a portion.
I see.
So there might be some subtle basis.
Yes, I agree. Yes, in molecular anthropology, it could happen. That is actually true. But you see, actually, this is enough to conclude one important thing. This is what actually I want to tell you about. Yes. Yeah, that's correct. Yeah, but this is the cobordism. Yes, this is different from what I'm talking about. Yes, but actually, I mean, it is. I mean, I agree with you that the cobordism actually can give you an even bigger anomaly, but it is very challenging to understand it up to now for me. Okay, how you are actually going to match the anomaly in the IR? It is still, I believe, still an open question. Yeah. So. Yes. Yes, yeah, of course. Yeah. In what sense? In one sense, it doesn't have fermionic operators. Uh-huh. No. Well, actually, I mean, this theory is bosonic. It doesn't have gauge invariant fermionic operators. Yes. Yeah, but this is. Yeah, there are no fermionic operators. Yes, there are no fermionic operators, right? Oh, very good. Very good. Yeah, great. Yes, right. You are right actually about one thing. You are right. You are telling me that psi bar, okay, is the most plausible condensate that can match the anomaly. I agree, but this is not the only one. I tell you why. If this were the only anomaly that you knew about, you could say that I could match the anomaly for fermion condensate. Right, I cannot write. I cannot. Okay. Yes. Yes. I agree. I agree. I agree. I am talking about how you actually going to match the anomaly in the IR by condensates. Which condensate? What is the minimal condensate that can match the anomaly? This is the question I'm trying to answer.
So what is the pattern of this? Which symmetry is followed? In order to ensure the max.
Oh, yes, very good. Yeah, so it has actually, so the discrete chiral symmetry has to be broken completely. This is the idea. You see, okay, this is what actually the new anomaly tells me. The old anomaly doesn't actually require the discrete chiral symmetry to be broken completely, but the new anomaly does. And because of that, the two fermion condensate or the bilinear condensate has to form. Some scenario like that actually is excluded. So this is the new thing. Oh, well, actually, this is actually true for any SU even number. Yes, but for odd number, it might not be true. Well, actually, I mean, you might say that the bilinear condensates will always form, but the idea it doesn't have to. Okay, you might match some anomaly by higher order condensate without the lower order condensate. Yes, okay, yeah. If you just be naive, this would be the answer, but I want here to put it in some non-trivial statement. I want to like find some non-perturbative statement to say about the theory. For odd n, I'm not 100% sure, but actually it's not like it's not in my memory right now, but I don't think so. I agree. Yes, but it is not always constraining, I believe. But for all n or for even n? For all n? Okay, so maybe. Oh, we are talking about about the two index symmetric. You mean? Yeah, I agree with you. Yeah, for the two index symmetric, yeah, you are right. Yes, I agree. For the two index symmetric, you are right. Yes. Yeah. These are two fermion. These two index symmetric or anti-symmetric. Right. So yeah, I agree with you. Okay. I mean, for all n, for the two index symmetry is correct. What you see here, okay, without this CFU anomalies, actually, I mean, the phase is not maximal. This is the whole idea. Okay, so my second example is going to be chiral bosonic theory, which is SU8 with Weyl fermion in the two index symmetric and 3 Weyl fermions in the two index anti-symmetric representation. Again, the theory has an SU3 global symmetry, but cross U1 axial symmetry, but they are not faithful. Okay, so you have to multiply Z4 cross Z3. The theory also enjoys a Z2 discrete chiral symmetry that acts on psi and chi like this. It does actually, in this case, it does act only on chi or chi bar. And there is also a Z2 one-form center symmetry. Again, the way to find out about this modding is just by examining the compatibility condition on some manifold M4. And let us see now, okay, what are the new anomalies? So there are two new anomalies. There is a mixed anomaly between the Z2 discrete chiral symmetry and the CFU background flux. This is an e to the I pi phase. There is also a mixed anomaly between the U1 and the CFU background, which is given by this expression here. Now, assuming that the theory confines, again, this theory is bosonic, so there are no fermionic operators. And also, there is no TQFT that can match these anomalies. So you conclude right away that the discrete chiral symmetry has to be broken down to nothing. And the U1 has to be broken down to at least to ZQ, such that Q is a divisor by 16 in order to match these two anomalies. So the minimal choice in this case is that you have to assume that these two condensates don't vanish, the psi chi bar and the chi bar to the 4. And these two condensates actually means that this global symmetry is going to be broken down to SU2. Again here, you might try to match all the anomalies using these two condensates, but the CFU anomaly is cannot be matched with these two condensates. So this proposal, for example, is excluded with this kind of new anomalies. That is correct. That is correct. So at least, okay, these two have to be non-zero. Okay, otherwise, actually, you cannot match these new anomalies. So my last example is going to be the theory, which actually that I can put it on CP2 and I can discover a new anomaly. So you might ask me, okay, that you cannot actually put a Weil fermion on CP2. So how we are going to do that? Because CP2 is non-spin manifold. And the idea is to turn on a U1 background. So in this case, we are talking about some spin C structure, which is given by this spin 4 cross U1 modeled by Z2. So one example is if you take SU6 with a Dirac fermion in the 2-index anti-symmetric representation. Now, this theory actually is fermionic theory. So, I mean, maybe Misha will like it more. So again, the faithful global symmetry is you have to mod the U1 baryon by Z3. Now there are two new kind of anomalies. There is a mixed anomaly between the discrete chiral symmetry. This theory has a Z4 discrete chiral symmetry, and there is a mixed anomaly between this discrete chiral symmetry and the Z2 one-form center, which is an e to the I pi phase. Yet there is also one more new anomaly, which is a mixed anomaly between the discrete chiral symmetry and U1 gravity, which can be discovered only when you put your theory on CP2, which is a Z4 phase. The theory also has some kind of old anomalies. All the old anomalies can be matched by psi cube, these composite massless fermions, but this is not enough to match the new anomalies. So first of all, there is this new anomaly, which is the e to the I pi phase. And in order to match the new anomaly, you actually have to assume that the 4 fermion condensate doesn't vanish, which basically breaks the Z4 discrete chiral symmetry down to Z2. But yet, this is not enough to match all the anomalies because of this anomaly that you can discover on CP2. And you have to propose that the theory also has an emergent Z2 TQFT in order to match this new anomaly. Well, telling the truth, it is not clear to me actually what this what this gauge theory, what this Z2 TQFT could be. It is just discovered by trying to match the phases. Is Z2 preserving TQFT? Yes, exactly. In the infrared, it is the infrared. Yes, it has. Oh, I mean, if you you want to break the Z4 completely, and you match it. well, it is not actually clear if you. It is not clear to me that if you break the Z4 completely, you can match this this anomaly. You might, but it's not immediately clear to me. Oh, it is not minus. It is a mixed anomaly. You might actually break the chiral completely, but then you don't need actually, in this case, the composite fermion. Yes, this is a new proposal because you can always break the discrete chiral symmetry actually and match the anomalies automatically. But this is a new proposal, right? Similar in what sense? Oh, well, I don't know. It's just the dynamics that can tell you. Well, I mean, naively, I would think, yeah, I mean, you can always just break the discrete chiral symmetry and you will be done. Yes. But this doesn't, but since there is a proposal, okay, you might want to really check it. This one? Oh, this is actually, well, you see, what happens is that when you form the 4 fermion condensate, you break the Z4 down to Z2, but you still actually have some Z2 remnant, and in order to match this Z2 remnant phase, you will have to propose that there exists some kind of Z2 TQFT. Exactly. Something like that. Yes, I would expect. Yeah, exactly. All right. So maybe actually this will, I will, maybe I have to wrap up. So I mean, the second part of my talk should be about gauging, okay, this this Ithoff twist, but I don't think that I will have enough time. So let me just end it here by saying that this is just the first step. I mean, this is just one of the steps of classifying these new anomalies, and the hope is that we will be able to find more anomalies in order to put more constraints on our theories. Thank you. Right. Well, actually, I mean, this is just a Z2 phase that I can see it on CB2. And the proposal is just there might be some emergent Z2 TQFT that can match this anomaly. But the nature of this Z2 QFT, I must say that it is not clear to me up to now. It's not clear to me as well. Yeah, I mean, see.
Then we should thank Mohamed again.
I say a few words. I don't know, maybe I could show one. Okay.
Oh, so the.
I don't have to do that. Okay.
All right.
So just a couple of sentences. First of all, after so many years of external obstacles, and I
sincerely thank you, all of you who are still here in this room, for coming, for giving talks. Also, I thank those especially. And your talks show that, okay, despite all what, still grows and develops. Changed a lot, I would say, in the last 10 years, but it continued to produce with new results. And this is very good. Very good. I think so. One more thing, realize, but soon we're very rapidly approaching 100 years anniversary of the development. The first works on the water flow theory is mid-19th. Second interesting thing is that this year is the 60 years anniversary of the systematic treatment. It has been published in 1972, and it presented the first extension. Algebra in 4 dimensions, and also they have written down, they have found that published given in the case when the photon mass and photon gravity. Well, the work they had used, there were no superfields at that time. They just used the most generic SQ the most generic form, all value operators for this particular field that are not a huge number, to a huge number of equations and a small number of so 50 years ago, 50 years of lessons in that publication, right? Planning to organize a conference. On this day, we organize a conference. Now, supersedity changed. It's not 20 years ago, it was all expectation. Now, it will be more likely all expectations for so keep that in mind. It's going to be around the same time. Finally, the last I want to thank Ali, our assistant and developers. Fortunately, I could not show up because she got a comment 2 days ago. But we did a lot of work for I think they organized everything smoothly. We don't see them, but let's Journey back home with no problems, especially crossing the boundaries.
Let's take a look. Like you say, we have almost enormous time to speech. Please don't forget autos covers. Any other devices, don't rush that. Don't forget yourself.
See you next year. Hopefully. See you, Misha. Misha, will you cross the photos? Will you cross the photos? Yeah, I will. I will. I will.